session of Non-Associative Algebra Day. And our first speaker in this session is Marzia Mazzotta from the University of Salento in Italy. And she's going to speak about associative pentagon algebras. Over to you, Marzia.
Thank you. First of all, I would like to thank the organizers for today's invitation. And I want also to take this opportunity to compliment them on their dedication to organizing every seminar every Monday, and also a lot of conferences, a lot of editions also for a year, and for giving the opportunity to researchers from all over the world to share their results, their studies, especially to young researchers. I myself have been a speaker during one of Monday's seminar. I also attend a conference in Sweden, and I also have the opportunity to organize one of the edition in Lecce, in my university. So I wanted to express my gratitude to organizers and thank you again. So despite the title of the event, my talk will be devoted to associative structures that are named associative pentagon algebras. These structures are connected to an equation. I will show you in a moment what I mean. And essentially, my talk is based on the following papers. The first one is actually my first paper that I wrote during my PhD with my supervisor, Francesco Catino, and another professor from my university, Maria Maddalena Miccoli. And it is on set theoretical solution of the Pentagon equation on groups. So this is the first part of the talk will be based on this paper. I will refer also to a recent survey that I wrote for communication in mathematics that is that collect some results on the set theoretical solution of the Pentagon equation, and contains also several open problems or ideas that can be developed on this topic. Moreover, the talk will be essentially based on a paper that I wrote with Agata Pilitowska, a professor from Warsaw University of Technology in Poland. And it is a preprint, so already submitted. And last year I visited Warsaw, so I went to Warsaw and visited Agata. And I proposed her to study some stuff related to the Pentagon equation with her. And I was glad to work with her because I know Agata from I met her in several conferences related to the Yang-Baxter equation, so from other perspectives, and I proposed her my ideas on this equation that is somehow related to the Yang-Baxter equation, and she was happy to accept, and I think we obtained some nice results on this topic. And recently also Arne van Antwerpen, who is an assistant professor in Maynooth University in Ireland, proposed us some stuff related to these associative pentagon algebras. And in particular, he obtained some nice results in the finite case. So we decided to work together on this topic. And so we are working we are continuing the first paper with Agata. And so I will present some results that we obtained. But this is still a work in progress. So the Pentagon equation belongs to an infinite family of equations called polygon equations. It originates from the field of mathematical physics. And there is this nice paper on polygon equations by Dimakis and Müller-Hossein that contains some basics on this equation, among these the Pentagon equation. In particular, if we have a vector space V over a field K, a solution of the Pentagon equation can be considered as a linear map from V tensor V into itself. that satisfy this equation, where Sij acts from V tensor V into itself, so is another linear map. And for instance, with S12, we mean that S acts on the first two tensors and as the identity on the third one. S23 can be written as the identity tensor S, so we mean that S acts on the second and the third tensors. And S13 can be written as the composition of these maps, where here sigma denotes the flip operator. But essentially, we mean that S acts on the first and the third tensors in the product and as the identity in the second one. So the Pentagon equation appears in several contexts and also with different terminologies. So the main motivation in studying the Pentagon equation lie in this context. For instance, in representation theory of quantum groups, of algebras, theory of linear operators defined in a Hilbert space, or matrix factorization problem and discrete interpolable system, and so on. This list is not exhaustive, of course, but this is just to give you an idea of some context in which the Pentagon equation appears and also with which name. For instance, in the context of analysis, so we have these operators, linear operators, defined in a Hilbert space that are called multiplicative operators, but essentially they are solution of the Pentagon equation. But in my talk, I will focus on set theoretic solution, so not on solution as we see before, but on set theoretic solution. What I mean is that we consider a set X and a map S from X times X into itself that satisfy this relation with a similar meaning like in the case of the vector space. So we have that Sij is a map from X times X times X into itself. And here S12 is the Cartesian product of S and the identity on X. S23 is the Cartesian product of the identity and S. And S13 again can be written as the composition of these maps, where here tau is the flip map that exchanges the role of X and Y in the Cartesian product. The first hint for studying this kind of maps can be found in this paper by Kasashev and Sergev. As you can see, this paper is published in a journal of mathematical physics. Indeed, it is not an algebraic paper, I can say. But here there is the first hint for studying this kind of maps. Why one should study set theoretic solution? The reason is that a set theoretic solution of the Pentagon equation can produce solution to the vector equation. In which sense, if we start from a set theoretic solution, so a pair XS that satisfy the previous identity, we can extend this solution linearly to a solution Vs, where V is the vector space with basis X. And in particular, one can see that the set theoretic equation is in some sense reversed with respect to the Pentagon equation, because I mean that the Pentagon equation starts with S12, S13, and so on, while the set theoretic solution is S23, S13, and so on. But essentially, we can extend this map, so consider the vector solution of this equation, and then consider again this composition that I call R, that is the composition of the flip operator sigma, the solution S, and again the flip operator, and obtain a solution to the original Pentagon equation. So the main motivation in studying this kind of solution lie in this fact. So this is also common, for instance, for the Yang-Baxter equation. For people familiar with the Yang-Baxter equation, it is common to study the set theoretic solution for instance, for the Yang-Baxter equation, and then extends linearly to the vector space and get solution to the quantum Yang-Baxter equation, for instance. So this is a very familiar approach. So in my talk, I will focus only on set theoretic solution that I will briefly call solution. And if we start from a set X and we consider a map S from X times X into itself, we can introduce two binary operation that I call dot and star on X and write the components of the map S by means of these two operations. So, for instance, the first operation will be X dot Y and the second one X star Y. So if we impose that S is a solution of set theoretic solution of the Pentagon equation, what we obtain is an algebra X dot star in which what is important is that the first operation is associative, so X with the dot operation is a semigroup. And then we obtain other two compatibility laws that are equivalent to assuming that S is a set theoretic solution of the Pentagon equation. So a pentagon algebra will be a triple X dot star such that the first operation is associative and these two relations are satisfied. Some examples, for instance, if we consider a set, then the identity always is a solution. Here, of course, the dot operation, if we compute x dot y is equal to x for all x and y, and x star y is equal to y. For instance, the flip map is not a solution when the set is not trivial. This is, for instance, the main difference with the Yang-Baxter equation in which the flip map is a solution. So here, in general, it is not a solution. Or if we start from a semigroup X dot, we can consider an idempotent endomorphism of this semigroup that I call gamma and set x star y equal to gamma y for all x and y. And in this way, we obtain a solution that is exactly this map. In particular, of course, we can take the identity as gamma, the map identity on X, and we always get a solution. So if we start from an arbitrary semigroup, this is always a solution. Or in addition, if the semigroup is a monoid with identity 1, then this map always is a solution. And in particular, so gamma is the constant map of value 1. Other examples, if we take a set and two maps that are idempotent, F and G, and which also commutes, then this map written as first component is the first component is equal to F evaluated in X, and the second one G evaluated in Y is a new solution on X. And in particular, for people familiar with the Yang-Baxter equation, this is also a solution of the set theoretic quantum Yang-Baxter equation that is very similar to the Pentagon equation. Of course, it's more symmetric than the Pentagon equation because in one of the two members of the Pentagon equation, there is one member missing. So this is more symmetric, of course. And this map belongs to the class of Lubachenko solutions that satisfy the Yang-Baxter equation. Indeed, in this class of solution, we don't assume that are idempotent in general, but if we assume that they are idempotent, they satisfy also the Pentagon equation. And in 2020, with Francesco Catino and Paola Stefanelli from my university, we study solutions that satisfy both the equation because we note that there exist other solutions that satisfy both the quantum set-theoretic solution of the Yang-Baxter equation and the Pentagon equation. So the intersection is not empty. Another example, if we consider a group that uniquely factorizes by means of two subgroups and A and B, and we consider the projection maps that I call P1 and P2, such that every element of the group can be written as, every x can be written as P1x, P2x. Then this map, for instance, is a kind of solution that is in particular bijective. And if we look at the first component, so this one, we know that this give rise to a semigroup. And if we call this operation dot, we obtain that G endowed with this dot operation is a left group. Some basic properties of a solution, for instance, if we start from a solution and we consider the map R written as the composition of the flip map, so tau, S tau, what we obtain is a solution of the reverse Pentagon equation, like in the for the equation in for the solution, for the vector solution. In particular, if S is a bijective solution, for instance, like in the previous example, and we consider this composition, so bar S equal to tau S to the minus, because S is bijective, so we can consider the inverse mapping, tau, then in this case we obtain another solution of the Pentagon equation. So if we have a bijective solution, we can construct another solution by taking, for instance, this composition. But now the problem is to find a strategy to construct a solution, because I like the Yang-Baxter equation, for which there exist several algebraic structures that systematically give rise to solutions, like braces, cube braces, cycle sets, racks, and so on. In the case of the Pentagon equation, we don't have this approach. So the only possibility is to fix a semigroup that so to fix the first operation, and then to find the star operation such that the Pentagon laws are satisfied, so such that these two laws related to the both operations are satisfied. So, of course, the first idea is to look at the class of groups, because we are talking about associative structure. So, the first idea is to consider groups. From the paper by Kasashev and Sergev, what emerged is that in the case of groups, there is only one bijective solution if we start from a group G dot. The solution is exactly this one. That is the one in which the first component is exactly the operation of the group, so it's the multiplication in the group. And the second component is Y. So it belongs to the family of solution with the endomorphism gamma, as in the previous slides, in which where the second component is exactly the identity, so gamma in this case is the identity. But of course, this is the bijective case. But if we look to the previous examples, I recall before that if we start from a monoid, so also from a group, also this is a solution. Of course, this is not bijective. So when I started my PhD, our first idea is to try to describe all the solutions starting from a groups in the non-bijective case, because in the bijective case, there is only one solution. And looking at also small examples, what we get is that there were several solutions that can be constructed also with small groups. And fortunately, what we obtain is a complete classification. Indeed, I will show you now the classification with also a sketch of the proofs because I think it's very nice. If we start from a group G dot, and we consider these ingredients that are a normal subgroup that I call K of the group G, a set of representative of the quotient, so that I call R, and a map me from G into R, such that its image for every x lie in the coset of K. Then the map written in this way, where again the first component is exactly the operation in the group, and the second one depends on this map me, is the multiplication of this element, is a solution. What is important is that vice versa, any solution can be written, can be constructed in this way. In which way? So assume that we start from a group G with a dot operation, assume that 1 again is the identity, and that the pair GS is a solution. So a solution that we write as usual with the two operations. So the first one is the dot operation in the group, and the second one is this star operation. Let us introduce for all x in G the map theta x from G into itself, such that theta x y is equal to x star y. So if we do this, what we obtain is that this set K, that is the set of all elements of G, such that the image of the map theta 1, where 1 is the identity of the group, evaluated in X is equal to 1, is a normal subgroup of G. In general, theta 1 is not an endomorphism of the group, but in this case, despite we don't have an homomorphism of the group, we obtain that this sort of kernel of this map is a normal subgroup. The image of this map is a set of representative of the quotient, and the image of theta 1 in X lie in the coset of K for every X. And in particular, every theta x y, so the second component of our solution, can be written exactly as in the converse part, where the map theta 1 has the role of the map me in the converse part. So, in the case of group, we have a complete classification of solutions. What we can say in general for arbitrary semigroups, even if we start from semigroups of small order, for instance, from order 3, in this case there are 18 non-equivalent ways to define associative operations. And if we compute the solution in all the solution up to isomorphism on these semigroups, there exist around 200 solutions. So what one can note, if we increase the order of the semigroup, of course, we increase also it increases also the number of solutions. So one strategy, as is also common for the Yang-Baxter equation, is to add some hypotheses on the map, on the solution, and try to obtain classification in this sense. What we know, what is known in literature is this. For instance, in 2020, Ilaria Colazzo, Erin Jespers, and Lukáš Kubat provide a description of involutive solutions. These are special bijective solutions satisfying S2 square is equal to the identity. I got a classification, a partial classification of idempotent solutions, in the sense that I got a description only not for all type of semigroups, but so only for some special classes of semigroup. So maps that are not bijective in general, of course, that satisfy S2 square equal to S. Moreover, with Vicent Perez Calabuig from Valencia and Paola Stefanelli, we try to extend what we have done for groups also Clifford semigroups that are semigroups very close to the class of groups since they are inverse semigroups in which every element admit a relative inverse, we can say, and such that the importance are central. So these semigroups has a behavior very close to the inverse of these semigroups has a behavior very close to that of groups. So we try to extend these results and we obtain two description of two family of solutions coming from these kind of semigroups. Very recently, also Marco Castelli provided a study, some results on commutative solutions that are another class that we can find among solutions. So here only we have this assumption that solutions are also commutative. Another preprint is available by Ilaria Colazzo, Jan Okniski, and Arne van Antwerpen, and they provide a description of finite bijective solutions. So with finite solutions, we mean that the set from which we start is finite. So when I went to Warsaw, so I visited Agata, we decided, she asked me if in these solutions, written of course as algebras, the second operation could be also associative. And what surprised me is that the answer was positive, because among the solution that I presented today, but also that I know, most of them are of this type. So we decided to look at these algebras. So we decided to call these Pentagon algebras associative, of course, and I will briefly refer to them as APAs. So we mean a pentagon algebra in which both operations are associative. From our examples, for instance, the class of solutions coming from an idempotent endomorphism of the semigroup are all APAs. So here, of course, the star operation is characterized by this map. So if we look at the table, the Cayley table of this star operation, of course, the rows are all equal. But also other solutions that do not belong to this class of solutions are APAs. For instance, if we take a set X with A, B, C, three elements, and we consider this associative operation, this dot operation, and as a star operation, this one, which the rows are not all equals, so we don't have a solution like in the first example. This is, for instance, an associative pentagon algebra, so this is an APA. It corresponds to a solution. Or if we look at the example with the group, so with the projection maps, if we assume that the subgroup A is central to elementary subgroup of the group G, then the two operations become like this, and we obtain an instance of APA. In particular, the first semigroup is a left group, and the second semigroup is a left cancellative semigroup. Some quick remarks. We can take also semigroups with both operations equal, and we can observe that we get an APA if and only if this identity is satisfied. For instance, if we consider a right zero semigroup, so a semigroup such that x dot y is equal to y for all x and y, then we get an APA. So it is enough also to take a semigroup in this case. And this corresponds to the trivial solution. So with the second component is equal to y. Or for instance, if we make some assumption on the star operation, for instance, if we assume that it is a band, that is an idempotent semigroup, this forces the first semigroup to be a right zero semigroup. And this is only the case. Of course, not all Pentagon algebras are APAs, so this is not a complete description of all the solutions of all APAs, of course, all of Pentagon algebras. For instance, if we assume that G is a group, and we consider as dot operation, not the operation of the group, but this one. So we assume that on the dot operation we have a left zero semigroup, and the star operation is equal to x to the minus y. We obtain a pentagon algebra that is not associative pentagon algebra in general. It is an APA if and only if G is an elementary abelian true group. And this is also consistent with the result that I got with Catino and Miccoli in my first paper, where we studied indeed a solution in which both operations are groups. And we obtain that in this case, the first component should be a left zero semigroup, and the star operation is an elementary abelian two group. So if we start from an APA, we can, like in the previous slides, we can translate the star operation by means of this map theta x, and obtain that that is basically the left translation in x. What we obtain is that an APA can be written also by means of these laws. Well, in particular, the first two are equivalent to obtaining a solution. And the third one is the translation of the associativity of the operation star. So, thanks to the third equality, so third equation, what we can say is that if we consider the set of all these maps, of these translations, that I call Tx, this is a semigroup, and it is, of course, a subsemigroup of the transformation monoid of all the functions from X into itself that we call semigroup of left translations associated to an APA. What we note is that if we start from an APA, some properties of the APAs can be translated in terms of the semigroup of translations. For instance, if the semigroup of translation is commutative, this means that the star operation in the APA is right normal. That means that x, y, z is equal to y, x, z for all x, y, and z. Or for instance, if the set of translations is a subset of the endomorphism of the set of all the endomorphism of the x dot operation, then this means that the operation star is left distributive over the operation dot. So of course this means that x star y z dot z is equal to x star y dot x star z. In our analysis, what we obtain essentially is that there exist two family of APAs in which our examples to which our examples belong. In particular, we obtain what we called a left trivially distributive APA, briefly LTD APA. That is an APA in which for all x, y, and z, x dot y star z is equal to x star z. So in this sense, it's left trivially distributive. And what we prove is that an APA is left trivially distributive if and only if the semigroup of translation is a commutative and cancellative semigroup. So if one wants to construct an LTD APA, can look to theta x map such that the semigroup of transformation is of this type. Thanks to this, we obtain several examples of LTD APAs. For instance, if we start from an arbitrary semigroup that admits a right identity, what we can say is that any APA with this semigroup is LTD. Or if the dot operation is a band, then again any APA is LTD. In particular, if we assume that the band is also semilattice, then X star, the star operation, is determined by some endomorphism, idempotent endomorphism gamma of the first semigroup. Or again, if we have an APA such that for some A, theta A is a bijection, then this is necessarily LTD. If we start from a finite solution that is also bijective, then if we are able to find an APAS, so if this solution gives rise to an APAS, so to an associative operation, such APAS is LTD, and in particular the dot operation is a left group. And this is also consistent, this is a consequence of a result that Colazzo, Kniski, and Van Aert obtained for finite bijective solution indeed. Or again, if we start from a semigroup that admit at least a left annihilator, so we mean that there exists an element L such that L dot x is equal to L for all x, then any APA constructed with this semigroup should be LTD. In order to study this kind of APAs, we introduce this family of semigroups that will help to characterize LTD APAs that we name PK semigroups. In particular, if K is a natural number and we consider this star operation, we say that this is a PK semigroup if for all x, y, and z it holds that x star y to k star z is equal to x star z. In particular, in the paper we provide a construction of these semigroups. We study also the variety of this family of semigroups. And what is important related to APAs is that an APA is LTD if and only if this semigroup, the star semigroup, so the second one, is a P2N semigroup, where N is a natural number. Similarly, for RTD APAs, so this is the other class that we investigate in the paper with Agata, we obtain similarly results. So we introduce a family of semigroups that will be linked to RTD APAs, and we provide several classes of examples of APAs in relation to the semigroup of translations that we describe. So an APA is said to be right trivially distributive, briefly RTD, if in this case it is right trivially distributive on the right. So x dot y star z is equal to x star z in this case. For example, if we consider the trivial APAs, so the semigroups that are Pentagon algebras, then we obtain RTD APAs. In particular, APAs that are both LTD and RTD are the one in which the star operation is determined by an idempotent endomorphism of the first semigroup. And if we look at the semigroup of translation, we can say that an APA is RTD if and only if it is a right zero semigroup. Thanks to this, we are able to say that a semigroup, for instance, if we start from a semigroup that admits a left identity, any APA constructed with this semigroup is RTD. If we start from a Clifford semigroup, as I said before, Clifford semigroup is an inverse semigroup, so each element admits a unique element, x to the minus, such that x to the minus x is equal to x to the minus x to the minus equal to x to the minus, and its idempotents are central. If we look at these Pentagon algebras, if we assume that the second operation, so the star operation, admits a right annihilator, E, that is in particular an idempotent on the first semigroup, then any APA constructed in this way is right trivially distributive. Or again, if the dot operation admits a list at right annihilator, so x dot r is equal to r for some r, and for all x in x, then any APA constructed with this semigroup is RTD. Also, for these semigroups, we found this family of semigroups that I call QK semigroup, in which this identity should be satisfied, that is x star y to k star z equal to y star z. Also, for this semigroup, in the paper we provide a construction of these semigroups. We study the variety of semigroups related. And we prove that an APA is RTD if and only if the star operation, so the semigroup X star, is a QK semigroup for all K. In our first paper, what we note is that so our natural question is to search for APAs that do not belong to the class of LTD or RTD APAs, because we didn't know if there exist other classes of APAs among our examples. But in the end, we found one example in a set of 7 elements that produce an APA that is neither LTD nor RTD. So it belongs to another class of APAs. In particular, if we start from a star operation, so a semigroup generated by a set of 2 elements A and B, such that these equations are satisfied, so the same group generated by these relations, then X is exactly this set. And if we construct 2 operations on the Cartesian product of X with itself, in which the dot operation works in this way. So the first component is exactly a left zero semigroup, so we take x1, and on the second component we take y2. While the star operation is defined in this way, and it essentially depends on only on the second component, so only on y1 and y2. One can check that this is an APA, but this is neither LTD nor RTD. And in particular, the first component is a rectangular band. So it is a particular idempotent semigroup. So in the ongoing project with Agata and Arne, we are studying a class of APA that we name rectangular, to which the example of the previous slide, of course, belong. And this is the class of APA, x dot star, in which this identity is satisfied x y star z equal to x dot y dot x star z. The name rectangular is because if we start from a rectangular semigroup, so a semigroup such that x dot yx equal to x, any semigroup, any APA constructed of this semigroup is rectangular. Moreover, LTD and RTD APAs are all rectangular. And if we start from an LTD and an RTD APA, if we construct the direct product of these 2 APAs, what we obtain is a rectangular APA. Also, for this class of semigroups, we introduce a family of semigroups that we are currently investigating, that is the class of BK semigroup, in which that satisfy this relation, so xk star y star z equal to y star z. And we prove that any APA is rectangular if and only if the second operation, so the star operation, is a B2K semigroup for all K in N. What is important is that what we proved is that every finite APA is rectangular. So for this reason, all the examples that we found in the paper with Agata are, of course, all LTD or RTD. So because we work especially with the finite case, but we also have examples so in the infinite case in which we have rectangular APAs. So for now, we have the proof only for the finite case, but of course, the future goal is to try to extend this result also in the infinite case. What we can say about the semigroup of translations is that if we start from a finite rectangular APA, then the translation semigroup, sorry, there is a mistake here, is a right group. Moreover, we can say more also because if we start from finite APA, and for every element of S, we consider this set, that is the set of all x in S, such that theta square, theta x2 square is equal to theta e square. These sets are very important because they constitute sub-APAs in our APA, and they are all LTD. And in particular, they give a partition of our set, of our APA, in the sense that S can be seen as the union of these LTD APAs, and these are pairwise disjoint. So in our future work, we want to understand better these algebras, try to extend our results also in the infinite case, and try to say that maybe that all APAs are rectangular. We don't know, so we will see. This is all, and I thank you for your attention.
Thank you very much. Do we have any questions? Any comments? Presumably, as well as commutative solutions, you can consider co-commutative solutions. Is anything known in that case?
There is no description for co-commutative solutions, no. My knowledge, no. But there are several examples also of commutative solution. I mean, Marco Castelli described only the commutative ones, if I remember. On co-commutative, I don't know.
Oh, okay. So they can be both.
Yes, yes. If I remember, they are related to vector solution on Hilbert spaces, so it could be interesting, of course, yes.
Any further questions or comments? Okay, well, can we thank the speaker again for a very interesting talk? Thank you very much.
Thank you. Thank you.
Okay, so we will start the next talk in about 12 minutes' time.